Hi, this is Dave Cole, and I'll be your instructor for Data Center Cooling Best Practices. This is part one of two modules talking about best practices. If you have any questions on this module, please feel free to use the question and comment box, and let's get started. What we're going to cover in this module are a couple topics. One is calculating cooling requirements, so really going through a data center and calculating out how much cooling we need. This is something that you could actually be able to go back and probably in about 15 minutes or so, go to your own data center and calculate out the cooling requirements. Be interesting to see that because typically what we find when people go back and do this is they find out they have a lot more cooling than they actually need. So at that point then they can start to look at maybe there's some crack units I can turn off, maybe there's some money I can save as a result of what I found out. So we're going to give you the formulas for calculating cooling requirements, and then we're going to introduce the high density cooling problem, at least give you a flavor for what high density is done in the data center and introduce that as a problem. In the next module we'll talk about how do we solve that problem. So let's talk about how do we calculate the cooling requirements. It's important to know a couple things, pretty basic stuff. The total heat output in my data center is the sum of the heat output of all my components. So what are my components? I've got my IT equipment, right? So my servers and my network gear and so on. My UPS is going to generate some heat. Power distribution, so my PDUs and losses in my power distribution are going to generate some heat. Lighting generates heat inside of the data center. Just running the air conditioner, so my cooling itself generates some heat. And then I've got people inside my data center also generate some heat. So those are the things we're going to look at when we're trying to figure out how much total cooling do I need in this data center. So if I kind of break this out into components, typically my IT loads are going to be 70 to 90% of the heat output. My UPS might be 10 to 13%. My lighting maybe 9%. Power distribution 6%. People maybe 2%. Your mileage is certainly going to vary. You'll have differences in your data center, but just to kind of give you a feel for where the big heat source is in the data center. So let's go through a real life example. These are kind of industry standard formulas that are used to calculate the total amount of cooling. So if you went to a data center design company, this is what they would use to calculate how much cooling you're going to need in your data center. So let's go through some assumptions here. I've got a 5,000 square foot data center. I have a 250 kilowatt UPS. Okay, so that's an important component. And that UPS is about 30% loaded right now. So about 75 kilowatts of my UPS is actually being used. I have a 20-person staff, so I'm averaging about 20 people in my data center. Probably a few too many people, but for our example, that'll work. So let's go through and calculate out how much total heat is my data center generating. So let's start with our UPS heat output. And here's the formula for calculating how much heat is being generated by my UPS. I start with my fixed loss factor. Remember, when we turn on a UPS, it's going to generate some electricity. It's going to generate some heat as it consumes electricity, right? So just turning it on, even if I don't have anything plugged into it. And that fixed loss factor is based on the size of my UPS. So here's the calculation. I take my total UPS capacity and I multiply that by 0.04. So in this case, I have 250 kilowatt UPS. I multiply that by 0.04 and I get 10 kilowatts. So my UPS, just turning it on, is going to generate about 10 kilowatts of heat output. Now, as I use more and more of my UPS, I get a loss proportional to my operating power. So in this case, I'm going to take my total IT load and multiply that by 0.06. So where do I get that IT load? Remember, I'm using about 30% of my UPS. So I'm using 75 kilowatts. That's my IT load. I'm going to take my IT load, multiply that by 0.06, and I'm going to get 4.5 kilowatts. Total those up, and my total UPS heat output is 14.5 kilowatts. Okay, pretty straightforward. If you have multiple UPSs, you would sum up all of your UPSs. Let's look at the power distribution heat output. Again, I have a fixed loss factor and I have a loss proportional to operating power. So I take my total UPS capacity and I multiply that by 0.02. So in this case, 250 kilowatts multiplied by 0.02, and I get 5 kilowatts of heat output. And then my loss proportion to operating power, I take my total IT load and I multiply that by 0.02. So in this case, 75 kilowatts times 0.02, and I get 1.5 kilowatts. I add those up and I get 6.5 kilowatts. Again, in this case, if you have multiple UPSs, you would sum up all of your UPSs. So that's taking care of our UPS and our power distribution. Let's look at lighting. I just take my entire floor area, 5,000 square foot, figure about 2 watts per square foot. So I get 10 kilowatts of heat output by my lighting. My heat output due to people, about 100 watts a person. So if I have 20 people in my data center, that's about 2 kilowatts of heat output. I sum up all of these. So my IT equipment is just how much of that UPS I'm using, 75 kilowatts. I have 14.5 kilowatts for my UPS, 6.5 kilowatts for my power distribution, 10 kilowatts for lighting, 2 kilowatts for people. I total all of those up and I get 108 kilowatts. That's the total heat output in my data center. That's how much cooling I need to provide. So again, I only need a couple of different numbers to be able to make these calculations. I need to know my total UPS size. I need to know how much of the UPS I'm actually using, that 30%. I need to know the floor size, how big is my data center, and I need to know how many people work in the data center. From those numbers, I can get a pretty accurate reading of how much heat output I have. Now I can go back to my cooling, add up all my cooling, and see how closely those match. Those should be pretty close to each other. Now remember, this total heat output does not include anything like redundancy, right? So I may need some additional units to be able to provide that redundancy. Other cooling considerations. If I have windows, exposed walls, or if I'm on the top floor and I have a roof, those may add to my heat load. I may need to do some supplemental humidification. When I do that, that does create additional heat load on my crack unit. So it decreases my overall cooling capacity of the unit, and it may require me to oversize that. So even though I said I needed 108 kilowatts, if I have to do a lot of humidification, maybe I'm going to up the size of my system. So 0% for a small system with ducted exhaust air return, up to 30% with systems with higher levels of air mixing. So a lot of it depends on how much air mixing you've got as well. A large data center cooling should be 1.3 times my IT load rating. Okay, so I want to make sure I've got plenty of cooling there, but I don't want to have twice as much cooling as I need. I would like it to be 1.3 times my IT load rating. And for redundancy, of course, I'm going to need additional capacity. So let's take a look, at least introduce this high density cooling problem. So in the past, we had data centers with average rack might be 1, 2, 3 kilowatts of power, right? And that's how our data centers were designed. That's how our cooling systems were designed, was to address these kind of density requirements. Well, guess what happened? Now my data centers are averaging 5 to 8 kilowatts or more. The latest studies, some people are averaging 10 and 12 kilowatts. You have to cool those racks differently because of the higher density. And vendors are pushing even more and more higher density servers, right? So it's getting to be more and more of an issue. When we look at the power trends of IT equipment over the last 10, 20 years, you can see how those have really ramped up. So we're continued to increase the density of every area of computing, from communication servers down to tape storage and storage servers and workstations and so on. They've narrowed out a little bit, they've leveled out a little bit, but the density is much greater than it was, even 10 years or so ago when our data center might have been built. And just to illustrate how big a problem this is, it's a great illustration, I think. Here's a Dell PowerEdge 1855 blade server with 4 chassis. Rated value on that is 20,000 watts, which is 68,000 BTUs. There's an HP P-class blade system, 22,500 watts, 76,000 BTUs. So think about putting one of those in a rack. That's 22.5 kilowatts in one rack just by putting in one of these blade systems. And if I'm designed to be cooling at 3 kilowatts, now all of a sudden I have 22.5 kilowatts, right? I have to address the cooling on that differently. Here's a Sunfire E25K server, 25,000 watts, 85,000 BTUs. And here's an HP H-class blade system, 32 kilowatts, 108,000 BTUs. 108,000 BTUs for that one system. Here's a Weber Genesis barbecue, 26,000 BTUs. Now remember, this was designed to cook meat, right? And it's only got 1/4 of the heat energy output of my IBM H-class blade server. Right? So these are the types of systems that we're trying to cool now using our existing cooling systems, which were designed for 3 kilowatts. Right? This has 10 times the amount of power draw on this. So it really is a big issue. And the next module we'll talk more about how do we solve this issue. But I wanted to at least introduce this issue. So when I look at total cooling in a data center, that's one thing. But now I also need to look at high density cooling and how do I address that. If you have any questions on this module, please use the question and comment box. And thank you very much for joining us.